Video is about uniform motion, and it's a part 2 of a 3-part series. So if you watch part 1, then you know we're going to use the formula D equals RT, which is distance equals rate times time. And again, uniform motion just means that it's a constant rate, a constant speed that doesn't change. So we don't think about deceleration or acceleration, it's just constant rate, which is virtually impossible, but we're going to assume that these rates are perfectly constant. And this type of question has a different form. It is D1 plus D2 equals N. So in the previous video, we saw D1 was equal to D2. We were talking about equal distances. But in this video, we're going to talk about distances that are not equal, but they add up to some number. So let's read this example. At noon, the horse and buggy headed north at 8 miles per hour. 2 hours later, the roadster headed south from the same location at 35 miles per hour. At what time? So our answer needs to be in time, which will be hours. Will the horse and buggy be 102 miles from the roadster? So what's happening is we have two different things that they're diverging from the same location. So I'm going to draw a little point that represents the place where they are. And let's say the horse and buggy is going north, so I'm going to put DN. And then the roadster is going south, so then I have DS. And these are not necessarily equal distances, but we know that they're going to have to add up to 102 miles. How do we know that? Because we're going to assume that they're 102 miles from each other, and we're going to find out at what time that's occurring. So the equation for this would be dN plus ds equals 102. And you could use whatever subscript, whatever letters you want. You could do dh for horse or dr for roadster. It doesn't really matter. But I'm going to write under my diagram, what do I know? So I know that the rate of the northbound, which is the horse and buggy, is 8 miles per hour. I know the rate of the roadster, which is going south, is 35 miles per hour. And I don't necessarily know the times exactly. Well, maybe I do. So if we look here, the horse and buggy left at noon. That's 12 o'clock. And then the roadster left 2 hours after, 2 p.m. So what we want to figure out, since we don't know the times, we at least know the relationship between the times. So I could say that the time of the northbound, the time of the horse and buggy, is actually going to be 2 hours longer than the time of the southbound roadster. So whatever the southbound is, the northbound was 2 hours more. So I do 2 plus TS. All right, so now I can go ahead and start plugging in what I know. Like before, the D always gets replaced with RT, so this is really RN-TN plus RS-TS equals 102. And RN is 8, and TN is 2 plus TS, and RS is 35. And TS is just TS. That's going to be our unknown variable here. And we have, that adds up to 102. So now we can just distribute and solve. We get 16 plus 8TS plus 35TS equals 102. We can rearrange the equation a little bit. So we'll subtract 102, take away 16. We would have 86. And then we would have 8 plus 35, which is 43 TS. And finally, we divide both sides by 43 to solve. And we get TS equals 2, right? 86 divided by 43 is just 2. So this gives us an amount of time, but we're asked at what time will the horse be 102 miles from the roadster. So the TS represents the roadster's time because it was the southbound time. So what we're going to want to do is figure out what time is it now. So it was 12 o'clock when they started, and then it was 2 p.m. when the Roadster started, and now the Roadster, which is the southbound, has been traveling for 2 hours, so it's now going to be 4 p.m. So another way to think about this type of problem too is if you actually solve for t n instead, which is the time of the horse and buggy, that's going to actually give you 4 hours, and then you could just add 4 hours to noon because this is the one that left first and the Roadster left second. But either way works. We're going to look at a couple more examples of this type of problem, but with a little bit different circumstances. And if you want, I encourage you to pause the video and try it on your own, and then check back your answer with me. So go ahead and take a moment to read this example and give it a shot on your own. Draw your diagram, and then check back with me in a few moments. All right, so checking the answer for number 5. The question gave us the rate of the walking, they gave us the rate of the boat, and they gave us the total distance and the total trip time, and they're asking how far. So our answer needs to be the distance of the boat. So I needed to solve for dB. I drew my diagram to indicate they walked, and then they took a boat in the same direction. The whole trip added up to 42. I wrote down my rates. I wrote down the relationship between time, and then I plugged everything in. At the end I ended up getting T sub B, so the time in the boat was 13 over 4 hours. And then I finally plugged that into to get to dB, which I know is the rate of the boat times the time of the boat. 13 times 3 is 39, so that's my answer. Sometimes our intermediate steps like this will have a fraction or a decimal. If you have it a fraction, I recommend that you keep it as a fraction because if you do a decimal and you end up rounding it, your answer might be a little bit off. So let's do one more example. Again, I encourage you to try it on your own and see how it goes, and then check back with me in a few moments to see if you got the same answer. All right, so checking the number 6, the answers are rate 1 and rate 2 are 30 and 40 miles per hour. When I set it up, I used D1 and D2 because there were no names or no initials to differentiate these two wanderers, but I did know that one of them was going 10 miles per hour faster than the second one, so I knew to just say R1 equals 10 plus R2. I could have also said R2 equals 10 plus R1. Either way, I would have ended up with the same two answers. And then T1 equals T2 equals 1.5. I got that because they left at 2 p.m. and from 2 p.m. to 3:30 p.m. that's 1.5 hours. And then plugging everything into my equation, I was able to solve for rate 2 and then solve for rate 1. All right, let's do one more example of this type of uniform motion problem about the northbound train left at noon. Go ahead and try to draw a diagram, try to solve this one on your own, and if you pause it, you can check it in a few moments. All right, let's check the last example, number 7, with the trains. So I drew a diagram to indicate one train's going north, one's going south, and their distances must add up to 315 miles since they're 315 miles apart. I wrote down the rates. I knew that the southbound was 15 miles per hour faster. And then I figured out the times. Looking at the times, I know that the northbound left at noon, and then we're stopping the time at 5 o'clock, so that's 5 hours travel time. And the southbound left 2 hours after the northbound, so the southbound was only traveling for 3 hours. And so once I plug everything in, I can just go ahead and distribute and simplify and solve, and I get southbound 30 miles per hour and northbound was 45 miles per hour. So I hope this is helpful. I have one more video in this series that's going to talk about uniform motion with a different type of formula, but also using D equals RT.